and so that is mainly for the structural design. Yeah, what happens when you do a water hammer, in addition to the static head that you have some other pressures that you need to consider in the structural calculation of yours, So what you do once you find the diameter of the penstock, for the structural analysis, you determine the thickness of the pipe. Once you do your water hammer analysis, then you can do the thickness calculations, because you will need to know the pressures and everything else. But there is also another thing, that if there is a surge tank, there is also pressure from that into the penstock. So you can mention that, but pictures, because they are most important. Let me information that the art you will not be able to learn totally in schools. You will learn that mainly from your projects, from your work experience, and from many other sort of works that you are doing from different people. Every time that you do a project, you learn a little bit more. Every time you do a different project, then it gives you a better idea. There is still the same energy calculations, the same formulas to calculate power, everything is the same. But when you do a project, that is not sufficient. You need to know other things, but then these other things, one part is to get information about different sites and different types of project, but the other part is that you also need to know and get information on other areas of engineering. Like the first thing that you do is to select the best site, because you want to build the dam so it is sound from a technical point of view and also feasible from other points of view, including or especially from economical point of view. So if you have a location where you want to select a dam for a high-head hydropower plant, if you go to see maybe between these two areas where is the best place, the first thing that you do is to look on the topographic maps. What do you look in the topographic maps? You look for a location where the valley where the water is flowing is narrow, but then in the back the valley is large, so you can create a big reservoir, right? This is not really the case for low-head plants, because in the low-head plants you are not really creating a reservoir. Maybe you do for a small volume, but the main thing in the low-level case is just that you built a small structure to impound the water a little bit higher. But then here, as I said, you look for somewhere where the valley is like narrow. That means when you build the dam, this dam, which may look like this, like a concrete dam or something, then you use a small amount of material to build the dam. And also from this information, if the valley is something like this, then you see there will be a big dam, a very lengthy one, for the same amount of water to be stored. If we are talking about very mountainous areas with rocky cross sections, that may be good for a concrete dam. But if you find something that it is not really rocky, don't try to build a concrete dam. You should look for an earth dam, rock-filled dam, earth-filled dam, because normally it is a good idea that the type of material that you select for building the dam, this material matches with the natural material at the bottom of the banks of the river. Because in here, if you design a concrete dam, the water may seep through at the bottom, and then the concrete dam will not be worth anything. Underneath it will be eroded, and the whole concrete dam will collapse. And it will be difficult to sort of bond the concrete with the other natural material, which could be sand, clay, or something, but it's still sort of pervious material where some type of seepage still go through. So in here it would be better if you design an earth-filled dam like this, where you may use a clay core in between and then some other material here and there, and then if there is water seeping through, water can also seep through the dam itself. The only thing is it needs to be controlled. It has to be under control, and that is okay. But if this is like a concrete dam up to here, and then the water is going underneath it, that will be very dangerous for the stability of the concrete structure. While in this case, if this is a concrete dam and these are rocks, then they will design it in such a way so the bond between the concrete and rock is perfect and nothing happens. And if there are some cracks or anything here, they will grout it. The grouting means that you push some sort of fluid, cement and clay and other type of material with high pressure in these cracks to make sure that everything is blocked. They do similar thing also in earth dam as well, because if there is a little bit of seepage under the earth dam or through the earth dam, it's okay. But if there is a big seepage, then it is not good for the stability of this dam either. So there might be some grouting to be done on this on the ground here as well. So you see, it is really important to where you select the location of these dams. Now, in terms of hydroelectric power plant, whether the powerhouse will be here just within the dam or not, that's again a different story that you need to study to see where to build the powerhouse. But in the case of low-head hydropower plants, normally you are not looking for a big reservoir to store water, because in many cases they are run-off river schemes, which means that the water comes in the river, goes through the turbine, and passes, leaves. There is no big storage, maybe just a little bit. In here, as I said, the only thing we do is to raise the water level to some extent, or as much as you can. This is, let's say, the bank of the river, if this is a cross section like this. So in here, you are not really building a big dam. They are called weir or barrages or type of structures that lifts the water surface so you can create some height between here and the downstream water level that you can use it in the turbine if the powerhouse is here to produce some electricity. So Again, from site selection, this is also important, but on the other hand, if you see the plan, it is always good that you find a location that if you design the powerhouse, there is still room for the overflow. Okay? So you should select that type of cross sections where if you design the powerhouse, it is not going to cause any problem to the flow during the flooding time or when there is a higher water level. And then there is no sort of a standard that you do it this way or that way. It all depends on that specific location and on the specific project. And you can see these pictures that they all have different sort of orientation in terms of flow, in terms of the location of the powerhouse, and in terms of building everything else to make sure that we get the things done. Like in this case, this is the powerhouse, and in here, this is like a transformation station, and the other part is where the extra flow passes this section. And the rivers that where they also have navigation, the ships are going back and forth, they also include a navigation lock, because once you have this barrage across the river, if the river is navigable, from that time on, the river will not, the ships will not be able to pass this structure. So they will design a so-called a lock. This is something that you design a separate type of basin, just like if they need to know what size ships navigate through this river. And then they use that information to size the basin for the ships. Like there is a room like this. If there are smaller ships or canoes, what happens, this has two gates, one at the downstream side, one at the upstream side. The water level at the upstream side or the downstream side is low, and at the upstream side it is high. So what they do, they have some valves. When the ships comes from downstream, the water level in the river and in the lock is the same. So the ship can get in. Once the ship is in, they close the gate at the downstream side. Then they release a water valve from the upstream side to fill this basin up to the level of the water at the upstream side. When it is at that level, then they open the gate at the upstream side so the ship can flow and navigate further, go to upstream. And when the ship comes from upstream, they just do the reverse of this, which means that once the ship is in, they close the upstream gate, they close the valve, and they open another valve for the water to go downstream. So then in the basin, it gets down, down, down. Whenever it is the same level as the downstream water level, they open the gate so the ship can go downstream. So if this is such a river, then you have to include a navigation lock. But also from environmental point of view, you have to include a fish ladder. That means that there are sort of little steps and a small amount of water is flowing here. Okay, this is the water surface. And this is like the upstream side. This is the dam or whatever. So if a fish wants to go from downstream, they can go through this easily, no problem. But you have to provide that in your design, because otherwise, from an environmental point of view, this design will not be accepted. So there should be something for the